Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about even, odd, prime, and composite numbers. These are pretty simple to talk about and give us a good example in understanding proofs, how to conduct them, something we need a little bit more exposure in before we can actually start talking about more abstract things. So to first understand how these work, we need to talk about factoring. We'll be talking about mainly positive non-decimal numbers. These are called natural numbers. We'll talk about that at a later point in time. But the idea is if we can divide a number x by some other number y, then we say that y is a factor of x. So in this case, you can always divide x by x and x by 1. So x and 1 will always be factors. Let's just look at a few examples. For 15, its non-trivial factors, which are not 1 and x, are 3 and 5, since it's literally just 3 times 5. But now if you look at 56, we can write it as 7 times 8, or 2 times 28, or 4 times 14, right? So we have multiple factors. And one thing we'll notice is that even if we just had the first part, 7 and 8, those are the only factors, since 8 itself has factors of 2 and 4, 2 and 4 will also be factors of 56. So there's kind of like a ladder being built up. It's not really a ladder, it's more like a tree root. At the top you have the numbers, and you can keep breaking it down and down and down. So all the factors are 1, 2, 4, 7, 8, 14, 28, and 56. Now we want to talk about even and odds, right? Of course, this should be something that we know, right? So is 3 even? Of course not, it's odd. But what about 3.5? Well, 3.5 is not even or odd, right? Anything with a decimal, we can't really talk about even or odd. It doesn't really make sense. And negative numbers are fine, so negative 4 is even. That's fine, negatives are allowed. So how can we formally define what it means for a number to be even? And it's actually pretty simple. If you can divide it by 2, or if 2 is a factor. And if this is not true, we call it odd. So this means that we can write out an even number in the form 2 times k, where k is a smaller number. So if you look at this example right here, 14, we have that 14 is equal to 2 times 7. So the idea here is that 2 is a factor of the number that we have, or we can write it as 2 times something else. So in this case, k is equal to 7. If we were instead to choose negative 42, well, we can factor the 2 and then get k is equal to negative 21, since 2 times negative 21 is negative 42. This doesn't actually work for odd numbers because we can't just divide by 2. So in order to fix this, we can just add or subtract 1. We'll just go with adding 1. So an odd number can be written in the form 2k plus 1, where k is another smaller number. So for example, 29 is equal to 2 times 14, and then we add 1 to it. So in this case, k is equal to 14. For negative 35, k is equal to negative 18, because negative 18 times 2 is negative 36, plus 1 is negative 35. This all comes down to this idea of factoring. If we can factor a 2, that's an even number. If we can't factor a 2, that's an odd number. But when we can factor a 2, we can write it in the form 2 times k. And if it's not an even number, we can write it in the form of 2 times k plus 1. That's the idea here. So that's what we formally mean for numbers to be even and odd. So how does this actually help us with proofs? Well, let's just do something simple, right? Prove that an even number times an even number is an even number. This should make sense, I think. Think about it for a bit, and we'll think about 2 different ways that we might go about this. So strategy 1 is just straight up brute force, right? We first notice that an even number ends in either 0, 2, 4, 6, or 8, and then just multiply all possible ending combinations, and we'll see that it always ends in 0, 2, 4, 6, or 8. And clearly, since at the end we get an even number, since that's what an even number is. It ends in 0, 2, 4, 6, or 8. There's a few questions we might want to ask here, right? Why is it true that an even number ends in 0, 2, 4, 6, or 8? Like, it makes sense. It's obvious. It's something we'll be able to prove, since like all that matters about dividing by 2 is the final digit, and you just divide by 2, and then of course it just works out, right? But we need to be careful of what we assume or what we know, right? I mean, it's not a bad strategy. This is called case analysis. You go by every single case. And like, you might say like, oh, it doesn't really feel clever. I don't really know what that means, but this is one way you could go about it. But me, I like strategy 2 more. So we're going to take any 2 even numbers, let's say x and y. We're going to write x as 2 times k for some smaller k, and y as 2 times l for some smaller l. Because remember, this is by definition what it means for a number to be even. This is the way that we can express even numbers. Then let's just multiply them together. X times y is 2k times 2l, which is 4kl, but then we can factor out the 2, so we get 2 times 2kl. Okay, but 2kl is a non-decimal number. this should be the form that an even number takes. For example, if we replace 2kl and let that equal to, I don't know, like I, for example, then you'd have 2I, and 2I is an even number. So we must have that x times y is even. And clearly, since x and y were like random choices, they could be any even number. The multiplication of any two even numbers will always be an even number here. Okay, so this is a shorter proof. It works in all cases, but it requires some more technical understanding, right? Because we actually have to like work through the definitions and connect everything and make sure everything makes sense. And this type of proof is called a definition unwinding type of proof. It's a simple proof type, but the idea here is that we literally just write out the definitions of what we have and then manipulate our definitions to get to what we want to show. So we want to show that even times even is even. Well, what does it mean to have an even number? Okay, now let's just multiply them, and then, oh, hey, look, we have an even number at the end by our definition. And one thing here, we assumed that 2kl is a non-decimal number. Of course, this should make sense. When you multiply non-decimal numbers, they're non-decimal. And when you multiply by 2, it doesn't introduce a decimal. But we didn't necessarily prove this fact, right? So how do we know that we're allowed to use this in our proof, right? In this case, it's fine. It's not actually that big of an issue, right? This is something we're allowed to do. In other cases, we assume that clearly obvious things to be true. But the idea is, if it's something that's so easy and so simple that it doesn't really make sense to explain it further, and it's not exactly what's being asked, then it's okay to assume it, right? But something like that, it's better to like check in. Let's say you did write a proof and you didn't prove the fact that adding and subtracting or multiplying non-decimal numbers keep them non-decimal numbers. If somebody were to later come and ask you, hey, can you prove this for me? And you can prove it, then you still understand what's happening, right? Remember, that's the key goal here. Since I'm not marking anything or anything like that, you don't have to worry about, oh, is this going to get like a 10 out of 10? Of course, communication is important, but if you're able to understand the proofs and you understand, hey, this is something that seems easy, if you can make that judgment and later somebody asks you, hey, verify this for me, and you can, then that means you understand it, right? That's more important. Okay, here are just a few more exercises that we have here. So we can show that odd plus odd is even, maybe odd times even is even, and you can do the whole entire thing here. So these two methods, or these two methods of writing proofs, have different trade-offs, and there's different interesting parts of them. And communicating it is definitely like an interesting part of writing proofs. We should think about, okay, which method makes sense to me and which method's the easiest way to communicate our ideas. Remember, we have two objectives when we're writing the proofs. We need to understand our proofs and we need to communicate our proofs. We need to convince ourselves that a fact is true. So you can either do this by intuition, working through the problem, or literally proving it, right? Seeing like, okay, does this step make sense? Does that step make sense? Then we have to communicate our proof to somebody else. So we need to write in such a way that somebody else believes our proof. What we want is to write in a way where somebody can't poke a problem in your proof. They can't be like, hey, this step doesn't make sense. In practice, you only need to understand and prove something in one way, right? But you can always try and mix and match. Maybe you try one path and you're like, this doesn't really seem to be working out, or this isn't the best way to communicate it, and you try something else, right? And you should do multiple different paths, or maybe try to prove something in many different ways when you're learning, because maybe one method is worse, or maybe you're not really like convinced that a proof is true, and working through it in another angle helps expose light on the problem. So we're just going to run through one proof again, just another simple definition unwinding proof. Prove that an odd times an odd is indeed an odd. Okay, so once again, let x and y be arbitrary odd numbers. So we'll write x as 2k plus 1 and y as 2l plus 1. Then we literally just multiply it out, and using BEDMAS, we get 4kl plus 2k plus 2l plus 1. We can factor out a 2 from the first three terms, and then we get a plus 1. Then clearly in this case, if we let 2kl plus k plus l equal m, then we get 2m plus 1. So x times y is 2m plus 1. And this is literally the form that an odd number takes. So clearly the final thing that we have is an odd number. And since x and y were just any arbitrary odd number, it could be any one of them, we have proved that any odd number multiplied with any other odd number is indeed an odd number. So now let's talk about primes. These are more interesting, and we can get some very, very interesting results. And many of the things that we want to learn about in modern mathematics is literally about primes. So let's just look at the definition. We say that a non-decimal number p is prime if p is not equal to ab, where a and b is between 1 and p. So pretty much what we're literally saying is p doesn't have factors that are not 1 and p itself. We use p because it's prime, it's easier to think about. So of course the definition here is confusing, but intuitively think about the fact that, okay, all this is saying is that we don't have factors that are not 1 and p. So there are only two factors, 1 and p itself. We cannot write it in terms of other smaller numbers being multiplied. You can compare this with what it means for a number to be even, right? So if we let, in this example, p is not equal to ab, right? If instead a is equal to 2, well, then we can say that, oh, p is not equal to 2b. So p, if that's the case for every single b, then we show that it's not even, so it must be odd. Thinking about the relationship between primes and composites and even and odd kind of helps us bridge the intuition gap between definition, what we want to prove, just combining everything together. Let's just look at a few examples. 1001 is not prime because we can write 1001 as 13 times 77. 13 and 77 are factors of 1001, but 101 has no factors that are not 1 and 100 itself. And we say that a number that isn't prime is composite. So in this case, p is indeed equal to ab, or it does, you can write it as multiplication of two of its factors, and those two factors are not 1 and not p itself. Okay, what can we prove about these numbers? Well, prime times a prime is a composite. That should make sense because a prime times a prime, well, the prime numbers are literally factors of the composite number. That's easy. Let's try something else. We'll do x squared minus 1 is composite when x is greater than or equal to 3. This is interesting, but it might be a little tough. And just try it out, see what you can come up with. Here, because we're just introducing things, this is something that you should be able to do. All you need to apply is an algebraic identity, a little trick. And sometimes that's all we really need to do. So I'll go ahead and look at this proof. In this case, we're going to use the following algebraic identity. X plus y times x minus y is equal to x squared minus y squared. Then we have that when y is equal to 1, well, we can see that we can rewrite this x squared minus 1 squared as x plus 1 times x minus 1. Then because x is greater than or equal to 3, 1 is less than x minus 1, which is less than x plus 1, which is less than x squared. So we can literally write x squared minus 1 as a multiplication of x plus 1 and x minus 1, and both of those are factors that are not x squared and not 1. Thus, it must be composite, since we wrote it successfully in terms of two factors being multiplied. And indeed, we can use this technique for every single squared value, right? So if somebody ever comes up to you and be like, hey, x squared minus 484 is prime for every single value of x, you can prove them wrong. Like, you can actually just prove them wrong. It's not like, oh, this is actually my, no, you can prove them wrong, right? And stuff like this, like, seems really random. Like, okay, it's just trivia. Why would I ever need to know this, right? But it actually does help in different places, right? Such as cryptography and factoring primes, because factoring primes is used in cryptography all the time. Something as simple as this ends up being a very, very useful result. So we can easily check if very, very big numbers are primes or not, just by checking if we can take the number and then subtract a square number from it. If that didn't make sense, don't worry about it. And remember, always try out your proofs, and you need to play around and tinker around. Here's a quote that I know and remember, I think is pretty solid, especially in math. A master has failed more times than a student has tried. I don't claim to be a master yet. I'm still a student, and there are many people above me. But trust me, all you need to do is just try and try and try. And don't think that trying and being wrong is bad, or you're not making progress, or it looks bad. It's really hard to see progress in stuff like mathematics. At least when you're doing other things, you can be like, hey, look, I'm getting this many correct, or I'm doing this. But when you're doing proofs, that's hard to quantify. Don't worry, just keep it up, and I'll see you in the next one.